What I'm looking at today, we did 25. I don't have anything to add to that really. Um, we could look immediately at 26, but 27 sort of generalizes it, so he kind of suggests, he's basically suggesting to do 27 and then just look at this smaller case. So like for instance, if you believed this answer, in this case, L would be 2, so L minus 1 is just 1. So it's saying if you take the solution and you divide by n, when you take the limit, you'll get 1 over A1, A2. In this case, the L minus 1 factorial is just 1. So if you had 27 part 0 here, that is pretty much, that answer is 26. Also in 27.2, he starts to explicitly use this case where you only have two variables. Anyway, we could look at both. So the question is, on 26, for instance, maybe I'll start to like write out what a case would look like. We did one just yesterday with actually 3 variables, just 1, 2, and 3. So like 24, the question was, what's the number of solutions to this equation? When I say solutions, I mean non-negative integer solutions for x, y, z. And we got something like an is the closest integer to, I think it was like n plus 3 squared over 12. So, I don't know, we'll write it like that or something. 25 is maybe more general. It's an equation like that, where the A1 and the A2 are relatively prime. So to start working on that, you would do something like this. Get a generating function. And the idea is going to be, I mean, what we did for 24 was we had 3 of these factors and we did a partial fraction decomposition. On this one, I mean, it's a little more general because we don't have numbers here. I was going to maybe even try an example and just make sure that they're both like prime, or at least relatively prime. We could do like 3x plus 5y equals n. And then you'd be looking at this example. But anyway, the point is going to be that you can factor this out, like when you do a partial fraction decomposition on this, you're going to have one term, the largest term in the denominator is going to be a square. So you can factor out once all the time. You're kind of guaranteed that you can factor out 1 minus zeta out of each of these. So we're going to have, if you had L variables, oh, I meant 25 and 26, sorry. Because in 27, they change it to look like this. All right, they've got like L variables where the greatest common divisor of all these AIs is 1, is the condition there. Anyway, what I was going to say is, in this case, when you do this more general case, when you do the partial fraction decomposition, Oops, I didn't mean to do that. I meant here. You can see again, you can always factor 1 minus zeta, but it's going to factor like L times. So this will be your sort of largest term in the denominator in your decomposition. And then you have smaller order terms in the denominator over there. But yeah, another thing is that when you find this, like, you can find this coefficient because we know, there's other stuff here, but like, these other terms are effectively say you took one of these out from this guy. There's going to be a1 minus 1. That's the degree of the polynomial that's left. And that polynomial is also, it almost looks like a geometric series. It's 1 plus zeta squared all the way up to a1 minus 1. So you can factor that using a root of unity, I guess the a1th root of unity. And so what's over here is stuff that kind of looks like that. Or like this squared, up to a1 minus 1. And then you've got a bunch of other terms, for every variable that you've got. Here we've only got the 2. But I don't know how large they are, that's why I'm kind of stopping. But you get a bunch of terms like that come from sort of a complex factorization. So it's just like a partial fraction decomposition we did yesterday, but it's using complex numbers, just like we had some of the examples yesterday. But yeah, what I was going to say is your denominator, your common denominator is this stuff. If you multiply everything by that, all the powers of 1 minus zeta cancel, so you're able to plug in 1, and all the other terms will cancel. You'll get zeros in all those. On the left-hand side, you'll have the numerator 1, right? So we get an equation like 1 equals a oh, right, sorry, times whatever's left. And what's left is, actually I should have written it down explicitly at this point. So for instance, if you have 1 minus zeta to the a, you can factor it like this. 1 plus zeta squared, all the way up to a minus 1. That's how it factors. So what's here is, let's see, 0, like zeta to the 0 to zeta to the a minus 1, it looks like a terms, right? So if you plug in 1 to this, when we multiply by this and we get the numerator is like a times this stuff, is what I'm saying. Now there's actually 2 of them in this case. There's this one for a1, and then there's another one next to it for a2, but your common denominator has a term that looks like this and a term that looks like that next to it. So you get a1 terms from this part, and you get a2 more terms from this part. So we're getting this when you plug in zeta equals 1 into that identity. I didn't write the identity down, but it's the numerator that you would get if you expanded all this stuff, So we sort of immediately we do know what a is. It's always going to be 1 over the product of all of the AIs, even in this more general case. Now, let me look at a specific example and see if I can like cut right to the more general, a more abstract argument. So we have one part, because there's only two terms here, we only get two factors of this. Because we're doing a partial fraction decomposition, you get another one of lesser degree. And then you start with these other terms. The claim is going to be that there's some polynomial of degree lesser than this stuff downstairs. Yeah, that's right. Yeah, the claim is going to be you can do something like that, right? Like, we could split this up further, but this is you could write it this way, is what I'm saying. The stuff that's here. If we factored two factors of 1 minus zeta out of the denominator, you'd get these contributing to the partial fraction decomposition. And then everything else that's there can be sort of absorbed into this. And the coefficients on this term repeat themselves. I mean, if the c was 1, it's obvious because all the coefficients are just 1. But even if you had a polynomial here, this c of z is of degree less than that number, whatever that product is. And of course, again, in this case, a is 1 over 15. So I guess part of this is one thing that they say in the solution is this denominator, if you were to factor it, the stuff that's left divides this term. You know, if we do something like this equals our denominator, then q, because these roots, remember the roots we talked about, we're basically using roots of unity, and these are all primes, so the roots are distinct. So q here has distinct factors. But we also know that this product, each of these individually, this divides 1 minus zeta to the 15 because 15 is a multiple of 3. And the other one also divides 1 minus zeta to the 15. Again, because 5 is a divisor of 15. So you can divide this, you'll get a polynomial of lesser degree. But the point is, since it has distinct factors, and these two individual factors divide that, their product also divides it. I mean, when I factor this out, this stuff that's left has distinct factors and still divides this 1 minus zeta to the 15. So like suppose this was some and usually you would use better notation here, but yeah, my point is just going to be that this is what justifies, this division is what evidently justifies this this split of the partial fraction decomposition into two pieces. One that depends on just 1 minus zeta, the polynomial, like a polynomial of degree 2 in this case. So you get something like, I'm using the notation of the solution here, but you get one part that looks like this, where R is a polynomial, degree, I guess L. And then you get another part, I guess he called it S. Yeah, and we'll stick with L, where S is also a polynomial, but it's of degree, lesser than this product. And when you look at the power series expansion of each of these guys, because this is just degree L, the expansion, you have some coefficient here. Let's, I don't want to call it AN, but let's call it CN, zeta to the N, right? When you do that, because it's degree L, Cn is a polynomial of degree, I think it's L minus 1. If we think back, well, like this term right here, right? When you go to write that down, you start with this kind of function. When you take this guy's derivative, in this particular case, you don't get another number popping out. You just get this. But if you differentiate again, you will start to get numbers. You'll get, here we got 1 factorial. But if you do it again, you'll get 2 factorial. And if you keep going, you'll see what I mean. Like there's still a 2 there from before, you take a derivative and you get another factor. So you're getting factorials when you differentiate here. But on the right-hand side, we get k plus 1 z to the k is our series. So you can picture that as a factorial as well, but it's coming from the powers of z inside your series. They're growing. So here I took 1 derivative and I got 1 term. And that's correct. This is L. You only needed 1 derivative for that. It's basically 1 fewer number of derivatives for the number of variables that you had. So we have 2 variables in this case. This power is 2, and you took 1 derivative to get there. That's why we have, one lesser degree. So you get a polynomial in the variable. In this case, it's just k plus 1 is the polynomial. But then there's other terms here, and those are the ones that come from the rest of the partial fraction decomposition. So if we called that, I don't know, dn zeta n, the point is going to be is that the dn are periodic with period, whatever this product is. Now without the s there, it's obvious because you just get 1 for all the coefficients. So yeah, sure, that's periodic, I suppose. But upstairs we have a polynomial that's of degree lesser than the product here. So for example, like our example above here, if you had like the product here is 15, 3 times 5. So if you had something with degree less than 15, like say 1 plus zeta squared all the way up to 14, we're looking at a polynomial like this. I mean, this is probably obvious to some people. I realize there could be numbers there. I don't know. This is probably obvious if you're good at algebra, but I am not quite following. I would need to think about this. It's shifting. Each one of these terms is shifting it. I'm saying this is still the coefficients that you get are 15 periodic, if that makes sense. So obviously the constant times them, that's not a problem. Oh, well, it is obvious, isn't it? I can it's true by observation. Yeah, it's kind of clear, isn't it? Well, you're getting a bunch of series, and they just shift it by whatever that number is. And so every time you look at a specific location later on in the coefficients, like in the series, it comes from one of these numbers, and it just keeps cycling. So it is somewhat clear. This is why I was saying, like, if you're decent at algebra, you probably know this already off the top of your head. Just glancing at this, you're like, well, yep, that's going to be 15 periodic. But yeah, maybe I shouldn't. Sorry, I'm just thinking maybe I shouldn't do 1 in front of each of these. Maybe I should make it a little more general. Because yeah, 1 is boring, right? 1 is not really proving anything. Of course, you're going to get. But yeah, more generally, of course, if you had a0, a1, z, a2, z squared, etc., and you multiply it by some power series, and that one we can have just regular coefficients are 1 because it's coming from this type of term. So if the c on top is of degree, 14 or fewer, then anyway, when we take c, the polynomial, c of z, and we multiply by just this boring geometric series that looks like, sorry, it's not actually k. I meant to write, so in our example, I meant to write like 15k because it's zeta to the 15, it's zeta to the 15 that is the base of our power series. But anyway, so yeah, down here, a little more generally, we have something like this. And my thought was the coefficients are 15 periodic. And that's kind of the second half of the answer for where I'll come back and say what I'm talking about, but I'm just kind of reiterating some stuff in the book, in the solutions. So yeah, if you expanded this, of course, you get, well, should we start to write some out? You'd get a 0, I mean, this guy has terms like 1 plus yada yada. So you get all this stuff, right? You see one of those, you get itself. And then after that, you get zeta to the 15 times each of these, right? So a naught, zeta to the 15, plus a1. So now it's kind of obvious that it's cyclic, right? Plus a2, zeta to the 17, etc. Up to I guess 28. What's wrong with me? A14, z to the, is it 29? Yeah, wait, why am I blanking out? No, it's 29. Yeah, that's right. Anyway, so that is why it is periodic. It's kind of clear that it's periodic if you distribute this. Anyway, let me get back to why I'm babbling about this. Oh, hey. Hey, Peepo Frog. What's going on? Hey, Roan Bag. No, not quite. I'm thinking about the number of solutions of this equation where x and y are natural numbers. We're looking at this book. What's going on, Peepo Frog? Welcome in. So yeah, I'm probably gonna. Well, I'm done stabbing at that. I was just trying to remind myself what I was talking about. So this was just a silly example. One example. As long as you pick like primes, relatively prime numbers is the only condition. So what I was babbling about, I'm trying to like generalize it so I can understand this part. So here's a more yeah. I kind of wish this was real analysis. I'm not very good at this, but that's a good thing because like that means I'm learning something evidently. This is more like combinatorics, I would say, or even number theory. It started with combinatorics. Back then I felt comfortable, but then it became really complicated junk. So a smaller example of what we're talking about is like the number of solutions to this. When I say solutions, I mean non-negative integer x and y. So it came from, you know where it came from? Is the very first problem in this book says, in how many ways can you make change? And how many ways can you make change for a dollar, say, if you had pennies, nickels, dimes, quarters, half dollars, and you set the right-hand side to 100 cents, how many solutions would there be? Right? So it sounds like a simple question, and it's like pretty straightforward for you to count it. If you just sit there with some brute force, you could make a big tree or whatever you want to do. You can do it on a computer in like 10 seconds. But you can also come up with what's called a generating function, like a power series like this, whose exponents represent the sums. And that's actually pretty straightforward. It's not as mind-blowing as it sounds. It's like, and it's also a standard combinatorics trick. So like if I was trying to solve, let's make it really easy, x plus like 3y equals n, and I want to know how many solutions there are. Here, let me not write the series yet. If you do something like this, each of these terms represents a solution. Like this is x being 2, and this is x being 3, and and the number 1 is x being 0, right? So each of these corresponds to a solution, or a value of x. And then if you multiply that infinite series by something similar for the y's, this time I have a weight 3, so it's going to be z cubed. That's associated with y being 1. And this is going to be y being 2. And this is going to be y being 3. You get the idea. And now, when you multiply any of these, that's one particular solution that you've got, right? Like if you do z to the 4 times z to the 6, that's x being 4 and y being 2, and it gives you z to the 10. It gives you a sum of 10. So that means you could, if you were to look at the power series over here, the coefficients are the number, let's call them a. This is the number of solutions to this equation. Yeah, good stuff, right? Cute trick. Anyway, this is like some, I don't know, it's cool. I don't know, I don't think everybody sees this, even if you're like a math major. Um, Unless you took a combinatorics class, I don't think you would have seen this. Hey, thanks, Peepo. Well, that's what you think. Didn't you see me struggling through all this stuff I don't understand? So this first page was good. Honestly, a lot of the first few pages were good. I was comfortable. I was comfortable until, yeah, I was feeling good through all of these until recently, until I got to like, well, just basically the ones I'm looking at now, 2025. Like thinking back on these, they're not too bad. Well, the problem is, okay, so like he does more general one, like 22 is where I started to, oops, here it is. 22 is where I started to like fall off the map. He gives us a set of equations. It's not simultaneous equations. It's just he wants you to consider how many solutions to that, or to that, or to that. And it's like gives you a big list of equations. And so you do it the same way. You do the same thing. Like here's just a 1 and a 2, and this is a 2 and a 3. So you're just going to do the same trick. But this time you're going to add them all up. So I'm going to get not one series, but like, I don't know, n plus 2 different series. And then he did some little, here I'll show you. Then he did some little trick. Yeah, here's his answer for 22. It starts off with what I was saying, except for the numerator is a little fishy looking, right? Instead of a 1 up there. So I could explain that, but the point is, I was comfortable with this left-hand side. I got that answer. But then the right-hand side, he does this little telescoping trick. And I'm like, man, I never would have thought of that. I mean, now that I see it, fine, I guess I can reproduce it if you give me this exact question again. And the rest of it's actually not bad. From here to there, it's just a little bit of algebra. The rest of it's not bad. But getting from the answer that I would have written down to like that solution, it's like one of those little math tricks, you know? And then the other ones are the same idea. Like, I didn't show you 23 really, but the answer for 23 is same idea, like a bunch of sums of geometric series basically, and the numerator has been scaled somehow so that it shifts a little bit. The reason for the scaling, by the way, I was going to say, I said I was going to skip it, but I can tell you. Usually, if you wanted equal to n, like we were saying before, if you want n, you would look for the nth coefficient. So here, if you want n, you're going to grab the nth coefficient. But if you want n minus 1, well, that's not the nth coefficient, right? That's the n minus first coefficient, and that one's going to be the n minus 2 coefficient. So that's why he's scaling by zeta. He took his old series, instead of looking for the n minus first coefficient, he's going to scale it by zeta, or by z, so that it shifts it so that now he is again looking for the nth coefficient. And here he scales it twice. So this is actually giving you the solution to, equals n minus 2. And this one's actually giving you this. When you grab the nth coefficient of this, you're actually getting the solution to n minus 1. That's about it. And if that made any sense to you, that was a rough sketch of how you're solving stuff like 22 and 23, where it's the same kind of equation, the same kind of question, but he's got a series of these. He's got a bunch of these equations together. You just add them all together, and then you do something. That's the hard part. You add them all together. That part's pretty standard. That's like, yeah, that's some combinatorics trick, big deal. But on the right, how you get that coefficient, that's where I'm like, okay, that's going to take some work. Take some creativity to know the trick to do. Anyway, let me get back on whatever track I was on. 26's question was basically like, do the same question, but in general, where A1 and A2 are relatively prime. And so we start the same way. And then what he does to solve these kind of things is he does a partial fraction decomposition. That's how you get that. That's how you get a grip on this coefficient. It's like, what is that coefficient really going to be? Well, in the earlier cases where we had a sum of things, I don't know. It depends on the specific. You just write it down, and there's probably some sort of telescoping trick that allows you to get a grip on it. But for this one, it's just the one equation. What are we going to do with this? Because you're not wrong to think, oh, well, that's z to the a1k times z to the a2k. Can I do something with that? I mean, evidently you can, but I don't know what it is. These are infinite series. So yeah, this is hard, right? I mean, this is only multiples of, I don't know. I haven't thought very much about this because you don't do it that way. Like, say for this example, I would have, I don't know why I'm going off on this tangent because this is not actually helpful, but maybe it's good to sort of see why it fails. So that would be the first series for 3, and then you'd multiply that by a series for 5. And the reason I should stop right now is because you know what you're going to get is obviously any linear combination of 3 and 5 is what you're going to get in the sums, right? Because we sort of already said that. You're going to get all possible sums. That's what the exponents are going to be. I don't know how helpful that is because I mean that's what you get. That's the whole point. But like, what is it? What are the coefficients? You seem to get one for each. You get one for each combo, but like some of them come up twice. Every time we hit multiples of these guys, you're going to get multiple solutions, I guess. Anyway, so yeah, if we could count that in an easy way, we would certainly have answered the problem. Anyway, I'm getting off track. The way he does it is partial fraction decomposition. And I had some crazy long video yesterday doing basically this example. X plus 2y plus 3z equals n. So I had a super long example yesterday that went on for like, you could probably skip the first hour if you wanted to review it. The first hour was just me reviewing partial fractions in general. So like, for instance, with this guy, you would have a term that looks like this, and you would have a term that looks like this. Like you have the 1 minus z squared, you have the 1 minus z. And that's it for the terms that include 1 minus z. You can actually factor, for sure, you can factor 1 minus z from here and from here, one time. But then the rest of the stuff that's there, it doesn't split over the rationals. It doesn't actually factor. You know, like if you had 1 minus z cubed, you can factor once, but then you get something like this. And that, I don't think that's going to factor over the reals. But you could certainly factor it over the complex variables. So that's what we start to do. We do a trick like this where omega is a root of unity. So I'm claiming there is a complex number for which this is, it factors somehow, where w is some complex number. But if you're familiar with roots of unity, you already know this off the top of your head. This is going to be the cubed root of unity. I want to say 2 pi I over 3. And this is a number which, if you cube it, will give you back 1. So I spent way too long babbling about that yesterday. But you can generalize this. So if you had like 1 minus z to the 5, I realize that's not very general. But anyway, of course it factors like this. And the idea should be that you could factor it if you want with a different omega. It'll be, this time it'll be, I suppose, the 5th root of unity. Doesn't have to be a prime, could be any number at all. Anyway, you get the idea. This factors, and it's going to have certainly 4 terms. It would have to, right? Our previous one had 2 terms for the cubic. Anyway, I'm kind of spacing out here. Why was I talking about that? Well, we had this, and we were talking about doing a partial fraction decomposition. We know that this is a factor, so we're going to have one term that looks like that. And then the other stuff, you could think of it as multiple terms. But if you want to be a little lazy, it's some polynomial over this whole thing. Where this is a polynomial of lesser degree than 4. And the reason I'm bringing that up is because his solution for this general question is pretty much this. He says, well, notice that there's one term that kind of dominates, and then there's this thing which is periodic. I mean, it's not periodic, but the coefficients that you would get when you write out the power series for this part, those are periodic. So now that I've given you all this mystery, let me show you exactly what he's saying. Question, again, was, a simple case of the question is right here, where he says A and B are relatively prime. Can you tell me the number of solutions to that equation? Where, of course, natural number solutions for x and y. And he says, well, it's going to be by the square brackets, he means the integer closest to this number. So it's either n over a plus b or n over a plus b plus 1. It's one of those two. And that probably looks like a weird answer, but actually his answer for 25 fits the same kind of mold, believe it or not. And that's the one that I was saying we did yesterday, and it involves a partial fraction decomposition. Yeah. But instead of actually doing 26, we're going to jump ahead to 27, because it's the same question, but with L variables, A1, A2, up through AL. And I think basically the answer, or the question to that, the last part of the question is, show that this limit would be this. That right-hand side is basically that. So we have the product AB downstairs, and we have n to the power L minus 1. L was 2 here. So we have a single n in your answer, and it's divided by the product of those coefficients A. But he's saying if you have this instead, if you were to divide your answer by n to the L minus 1, if you take a limit, you'll get this coefficient. You'll get this number. You don't really see the factorial when you just have 2 variables, but we did see it for number 25. Here it's 12. Is 2 times 3 times 2 factorial. 2 times 3 times 2 factorial. Anyway, so I was going to try to tackle 27 today. But it's tricky. It's actually not bad. His answer is going to be very quick. So when you see this big mess, you start the same way. I did write it down. Good. So here's the question. Here's me pretending to jot it down, right? So 1 over zeta to the A1 times 1 over 1 minus zeta to the A2 times all the way up to 1 over 1 minus zeta to the AL. Let's say we did a partial fraction decomposition on that. Let's say we did. I don't really want to because this is all general and I can't really get very far, but I do know that there's going to be this term. There's certainly going to be L factors of 1 minus zeta, because you can pull one out of each one of these denominators. So this is sort of the biggest, it's the biggest term in the denominator that you're going to see on the right-hand side. Everything else will have lesser degree than L. In fact, everything else, because these were relatively prime, no one else shares any roots over here. Like when, yeah, this is what I mean. If you were to fully factor it over the complex numbers, right, it looks like this. These roots are not the same as these roots, right? As long as they're relatively prime. If you give me like 4 and 8, then no, all bets are off. There's probably going to be some shared stuff. But since since 3 and 5 are relatively prime, these are not the same roots. I realize, sorry, I used the same notation. I probably shouldn't have done that, but these omegas were I think fifth roots of unity, and these ones are third roots of unity. So yeah, I'm running out of observations. What was I going to say? You start here, you then do a partial fraction decomposition, and I guess while you're here sort of watching, I can explain another little neat thing. When you do that partial fraction decomposition, we get other stuff, right? B over 1 lesser and some other stuff. And then I said I got like lazy and I did a polynomial over, you could maybe think of it as the complex parts, but it ends up being like this for some reason. But we'll get back to that. But my point was going to be, you have this all equal to 1 over the product of stuff. So when you usually what you do with the partial fraction decomposition stuff is you say, if I were to add these fractions, I'll get 1 equals, right? We get an identity like 1 equals a times, and then you get some numbers here. Well, you get some stuff that depends on zeta, but you usually do some quick trick like let zeta be 1, or let zeta be omega or something, and a bunch of the terms cancel out. So what I'm going to do is plug in 1, and what's going to happen is this any terms, which is all of them except for the leading guy, any terms that have 1 minus zeta as a factor are going to become 0. So like at zeta equal to 1, we get 1 equals a. This one is the only one that survives. But what goes here is, well, remember this factorization we did? Everything looked like this. We pulled out 1, and then we had this term, or excuse me, this factor. Or maybe we also have this factor, right? We could have multiple of these. We've got 3 and a 5 and a 7. We've got a bunch of these things. So we might have this, and also we might have this product. But the point is, when you plug in 1 to this, or you plug in 1 to that, you just get an awesome number. It's just 1 plus 1 plus 1 plus 1. And it happens, well, if it's 5 you were factoring, it happens 5 times. If it's 1 minus z cubed, excuse me, 1 minus z to the 3 you were factoring, it happens 3 times. So for our example with like a1 and a2 and a3, you get something that happens a1 times a2 times a3 times. I didn't explain that very well, but yeah, in general, I said it like at the beginning of the video. You guys might not have been around, but I didn't actually write it down because it just feels like a mouthful. But it would be what? It would be like 1 equals a times, I don't know what to write here because there's going to be a big product of things. It's like 1 plus z to the a1 plus z to the 2a1 onward. And then there's another one that's, wait, that doesn't make sense because that's not what I meant. Damn it. That's wrong. Sorry. It's going to be this. It's just a regular geometric. But it stops at a1 minus 1 because we factored 1 minus z out of it. And then you get the next one, same thing, but it stops at a2 minus 1. And then, you know, etc., all the way up to z to the al minus 1. So that's why I'm getting this. That's why I'm getting this. So you actually have a grip on this number. You can actually find that without even, just in general, which already sort of blows my mind. But anyway, you don't have to actually do the partial fraction decomposition for this problem. You already know what the leading coefficient's going to be. So that's cute. The rest of them you don't. Okay, you would have to, especially like anything with a power of 1 minus zeta in it, other than the biggest one, that's kind of a pain to find. We did it yesterday, and we had to that was like the one we did last. I think we ended up plugging in, we just plugged in like 2. We just plugged in like a random integer. So it's doable, but obviously it's not going to be very doable for us in general. But the leading one is, and that's all we need for this question. Notice that 1 over dot, 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 that's what we just found. So the only other observation for this first part, for 27.0, to get the rest of this, you know, to prove that this is true, the only other thing we need is, this isn't the actual power series yet. This is just the partial fraction decomposition. So you're basically going from here into saying like, okay, if I had a bunch of fractions that looked like something over 1 minus zeta to some power, how would I write them as a power series? Well, super easy if it was this, right? You know this one. But if they're squares, we talked about this yesterday too. You probably already know this if you've had Calc 2. But this is a derivative of that. Just be a little careful with it, because there's like a double negative thing happening with the chain rule. But this is the derivative of that. And in fact, if you keep going, you start to get factorials, right? Like this is stuff to the negative 2. So when I differentiate it, I get 2 times yada yada, right? And if I do it again, I get 3 times 2 times whatever. So you're getting a little factorial. I wave my hands and claim that, but oops, I should have done it. I should have written down the 2. So I don't know. I'm writing down some of the easy stuff that we talked about yesterday. But this is like Calc 2 stuff. If you're familiar with geometric series and you differentiate term by term, you'll be able to generate these Taylor series expansions for this function on the left-hand side. Or I suppose if you ever looked at like log of, I don't know, I'm just thinking out loud. You could even do log of 1 plus x. That'll give you the same kind of behavior. If you look at the Taylor series expansion of that, but I'm just daydreaming. Anyway, so what he did was, I mean, what you usually do is you put this back in terms of z to the k. So now I can start at 0, I believe. Like here, when you plug in 0, you don't get anything interesting. You really may as well start at 1. So we're sort of re-indexing, so we start at 0. And then here is the same trick. You want to start at 0, well, then in that case, you're going to have a k plus 2 and a k plus 1. So same series. But that's how you would express this kind of guy, right? So like if you had L as your power instead of 3, you would expect, well, first of all, we got to move this factorial. We may as well move this over here as part of our coefficient. So for instance, an easy example would be if I take this cubed, we should have a 1 over 2 factorial, weirdly. I probably should have just put it next to the coefficients. And then there's a polynomial. If you're talking about 3 for your power, then it's a polynomial of degree 2. And also that factorial was 2 factorial. For us, we had a power L. That's our leading that's our biggest, in some sense, fraction. So we got the number a. It looks like this, and that's part of it. It's a times. But we've also got, I think we're also dividing by L minus 1 factorial. And then we also have some polynomial here. So I'm just going to write p of k. But we know the degree. P is degree L minus 1. Yeah, that's right, L minus 1. It's the same as that number. And that's just this first term. There is other stuff there. But that's sort of the one out front. Some polynomial, in particular, it almost feels like a factorial. It's k plus 2 times k plus 1. Or, in this case, I guess it's k plus L minus 1 times k plus L minus 2 plus times, all the way down to 1. So yeah, we do have other stuff here, but that stuff necessarily, it does the same thing, and this polynomial will be of lesser degree, because these are of lesser degree. So you've got this one chunk here where this is the biggest term, and there are certainly other terms, but let me just observe, other terms have lesser degree, smaller degree than L minus 1. And then we've got the complex part. And I don't want to spend too much time trying to make sense of it, because he doesn't in the solution. He does kind of a hand-wavy answer. But what we had done yesterday was, of course, this type of factorization over the complex numbers. And what he does in his solution is he basically observes that when you get coefficients for that, it will be periodic. Yesterday when we did it, what we got was like 2. So for example, with this question, this term contributed 2 cosine, and then it was basically the root of unity thing again. It was the same angle you would have had when you take the third root of unity. So we had 2 terms that came from cube roots of unity, and they show up here. They both show up here, but they simplified to just be like 2 cosine that. So we have a series of things that, well, the point is that this number is periodic. This one is 3 periodic. Every third coefficient is the same if you just looked at that piece, because we had a cubed root of unity. Every third coefficient here is going to be exactly the same. And I think that's enough for us to understand his answer. So yeah, what goes here is the complex part, but it's what he's gonna say is that this part is the coefficients are periodic in this product. He has a really terse way of answering things where he's like, he doesn't give you this page-long computation. He just says, well, it's a great way of writing, how it is. I think maybe it might even be more terse than Rudin. So I probably held off enough. I should show you this answer. Once again, what are we talking about? The AIs have a common factor of 1. I suppose that doesn't mean they're pairwise relatively prime, I guess, because he mentions that later. But in any case, the greatest common divisor of all of them together is 1. And then we're looking for the number of non-negative integral solutions for the x's to this equation, so the AIs are all the coefficients. And then he says, well, an is your solution. I can tell you that it satisfies this property. Where if you had this solution, if you divide it by n to the L minus 1, you'll get this ratio, which by the way is just the a value that we had, of course. And then this extra part, the L minus 1 factorial, I was saying that comes from when you take a derivative of a geometric series, every time you do it, you get an extra factor out front. So we're dividing by that factor, and that's how it ended up downstairs. So we basically just proved that part. If you followed most of what I was saying, you just saw a proof of this. And then before I switch to the back, because I'm just going to look at the answer for 27.1 too. I've basically been talking all about point 1 here today. Suppose they are relatively prime. Then in that case, your solution is a polynomial of degree L minus 1 plus a sequence that's periodic. It's periodic in the product A1, A2, AL. So that's about the only part that I understood. I was reading this stuff. I was working on it earlier. So now I'm showing you his answer. 27. From here to here is what you probably want to see. So he didn't jot down the first step. The first step is that, of course, if you were trying to get the solution, you're trying to find the number of solutions to this equation, you write down the product of a bunch of geometric series, basically. 1 over 1 minus z to the a1 times 1 over 1 minus z to the a2. Then he does, oh, here it is. He did write it down. Sorry, I thought he didn't write it down. You get this series. That would be your first step. And you're asking yourself, how can I get a grip on these ANs? Like, do I have a formula for the coefficient AN? Because if you do, that's your answer. That's the number of solutions. But the principal term, meaning the one with the largest, this guy, actually, I guess he wrote it down, sorry. The principal term, we noticed, has this for a solution for A when you do the partial fraction decomposition. And since they, yeah, this is where he was saying, like, the other terms in your partial fraction decomposition do not have more powers of 1 minus z. This is the biggest one. So the next one has 1 minus z to the L minus 1, but this is the biggest one. And then he trails off because he's basically done answering it. I guess I won't get into this because I talked about it the other day. He makes a little comment that doesn't really... He makes a little comment that, by the way, if you took the volume from your equation and you made it like a less than or equal to n, that volume would be this. And it's basically just if you're familiar with like U substitution, we're doing that but in multiple variables. And the multiplier you would get, you know, you usually do like U equals 2x, you get a half popping out, or U equals 5x, you get a 1/5 popping out. Well, for this thing, the Jacobian would be 1 over a1 times a2 times al. So that's where that denominator comes from. And then the L factorial, or the n to the L over L factorial, I want to say that comes from, that should come from just integrating. If you set yourself up like a big L-dimensional integral and just integrate from 0 to like 1 minus the previous variables each time. I had jotted it down like two days ago or something, but not super important, just a little comment that he made. Hey there, Hitch Streezy. What's going on? I'm scaring people with math today. So yeah, 27.1, is the one that I wanted to review here. This is basically what I had just been jotting down this whole conversation. So I'm going to wrap it up after this. Or maybe I should just attempt 27.2 on stream so I can get it over with. I'll just read through the solution on 27.2 because I don't really know it. But 27.1 I finally understood. So yeah, point 1 was the one that says like your solutions, number of solutions will be a polynomial in L-1 plus a periodic, a sequence that is periodic in the product of your relatively prime numbers. What it does is, when you do your partial fraction decomposition, you're going to have two chunks. You're going to have the one chunk that is like these pieces, where you've got powers of 1 minus z in the denominator. The other chunk is the complex part, like the part that involves using roots of unity to factor it. And he points out that it's going to be just some polynomial on the top divided by 1 minus z to the product. You probably can't really even see that. There you go. And so, I don't know, I guess I'll just let you read that. I can explain a little bit of this. Yeah, I have like maybe I already did, but I have like a quick comment about the divisor, but yeah, very short answer, not too scary. So today I was looking at this one. Like how many solutions, if the AIs are all relatively prime, how many solutions to that would there be? And I guess we're able to say this about it. AN is the number of solutions. That one wasn't too painful. He's just generalizing something that we did in 25. So 25 had like 3 terms, but they are relatively prime. This one has like L terms, but you end up with a formula that made sense back then too. It was the same answer. So today I talked about 27 and 27.1. And I haven't done 27.2, but it's not as bad as it looked. He's actually just doing specific cases. It looks like he's got like a whole page of answers, but yeah, that's actually the end of it, this whole page. He's just got 4 parts because he had 4 statements. So it's not as bad as it looks. But then here's these ones are cool. Points in 3D whose Cartesian coordinates are integers are lattice points, are called lattice points. How many lattice points of the closed octant? I guess we're in 3D here, so that's why he's able to say octant. But how many lattice points lie on the plane x plus y plus z equals n? So what is that like? I guess it's coming in at an angle. If you picture x plus y equals n, that's like a negative. Straight angles are Jesus. Equals added to equals. Okay. Yeah, so you get this thing coming in at an angle, and n shifts it up and down, and it intersects with some lattice points, but how many do this? This should just be an easy question, right? $28 would be like $28 would be like you look at this series times itself 3 times. This is the second derivative of the geometric series. So that's how I'm going to be able to jump to, well, there'd be a 2 there, but this guy has a formula like this. Let's see, normally you'd have a k and a k minus 1. And then the power would be k minus 2. So I'm going to shift that by 2 so that we can still start at 0. So this is the answer. I should have put n's there, but I feel like yeah, this should be, that's my instinct on number 28, is this formula. And of course he's going to be like, well, that's silly. Yeah, his answer was just, well, just put in, oh, sorry, you can't see it. Put in p equals 3 into this equation in 11 and 12. I don't know, man. Let's see. What was 11 and 12? Oh, I guess I was wrong. Did I read it wrong? He's saying it's almost just combinations. So like, if you had 3, confused, 28. Put p equals 3, oops, put p equals 3 into 11 and 12. What is, did I like read the question wrong somehow? Yeah, the second part I didn't notice, but just how many are not 0, that's should be an easy enough shift. Yeah, he did it differently. I must be wrong then, right? Well, not necessarily. He's saying he's saying you get a formula like this: 3 plus n minus 1 over 3 minus 1. So he's saying take n plus 2, choose 2, which is exactly what I wrote. Awesome. I didn't think of it his way, though. I did it almost analytically, where he approached it combinatorially. And then for 12, does make more sense to do the second part of the question. So the first part was do this, where the xyz can include 0. But if you don't include 0, I mean, I probably would have just done this and subtracted, like, but I don't think I don't know all the ways. Well, if you just have these 2 that equal n, isn't that just like n plus 1 ways or something? So I probably would have got something like, no, it is kind of annoying to count it. It's annoying to count it because you got like different cases. It's not just this is 0, this is 0, this is 0. It could be that these 2 are 0, so you're doing like 3 choose 1 or 3 choose 2. So you get a big block of cases here for the second part of the question where they have to be strictly positive. The way I was doing it is a little bit irritating. The first way was not bad, but if you avoid 0, that kind of is annoying. So maybe that's why he's saying to do it this way. Because for 12, I realize this probably makes no sense if you don't know what 12 is. But 11 and 12, the questions were, so 11 says, there are p people sharing n dollars. How many ways can you, oh wait, yeah, how many ways can you do that? So I suppose one obvious observation is some of them might not get any money, meaning we're including cases where one of them is 0. But other than that, it's very similar to this kind of equation. This is like we have 3 people and there's n dollars to distribute between them. So it's the same question, except p equals 3 in this case. And then part 12 was same question, but if they each get at least $1, how many ways can you do that? So, right, 11 and 12 are both like, that's pretty basic counting stuff. You could even ask these like in high school. I mean, they're somewhat challenging, but it's not over a high schooler's head necessarily. If you're familiar with combinations, it's not too bad. But yeah, the second case where we say they all get $1, I mean, in general, his first answer was this. The answer to number 11. And for number 12, well, now I can't remember, but probably should be able to reproduce it if I really was forced to. Anyway, that was 11 and 12, his answers. So 11, he actually did it like the hard way, basically the way we just sort of talked about. He constructs a series. Mine was 3, but in general, you could put a p here if you had p people that you were distributing these dollars to. And it involved negative binomial coefficients. It involved binomial coefficients where you've got a negative power, right? So if you look up, I mean, you're probably familiar with the binomial theorem, like people have been for hundreds of years, but then Isaac Newton came along one day and pointed out that you could even just use a real number up here. You'll still get a formula. So this time you get negative p choose k times, an alternating, something like that. So it's like you get k factors. Well, it does something fishy though. It goes like up. Yeah, I was never. Where is it? Here it is. Is he writing it? Yeah, he's sort of writing it. Yeah, he's writing this one out. These are the same. So like negative p choose k would be p times p plus 1 times da 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 up to p up to p plus k minus 1. So you get k terms. It's sort of what you expected anyway, right? When you take a combination. If you're doing choose k, you expect to get k factors. So we get k factors, but this time they start at p and they go up. And then downstairs you still do you still divide by n factorial, or sorry, k factorial in my case. I should probably spend a day talking about these. I brought it up before, but I don't remember I don't think I derived it or anything. I must have done something to justify it. Well, we just sort of justified it today. I was talking about this earlier because we kept dealing with stuff like this. And I was like, well, you take 2 derivatives of just a regular old, go ahead and write z, I guess. 2 derivatives of the regular old power series. Sorry, if there's a 2 there, you'd get this. So you can do that in general. That must be where he got it. Well, he extended it to all reals. I guess I don't see What's wrong with that exactly? Well, what's wrong with that is that I don't have a formula for that. I only have this. So I'm going to only be able to get integer powers. But I'm already impressed that I can get integer powers. Most people are familiar with natural number powers for this binomial theorem. Yeah, I don't know how you prove it for reals. This is what I was just... We're all happy with natural numbers. I think we can even prove it with natural numbers, right? If you just sit here, you can prove it by induction. So everyone knows that case. That's what I was mumbling, like, people have known this since like 1700. But then the negative case, I was always like, what? In fact, when I first saw this answer a week or so ago, when I saw these, I was like, oh, that must be a typo. And then I realized it's definitely not a typo, because like this is a negative power, so it's not a mistake. He didn't write. He is using negative. I mean, I remembered that there are negative binomial coefficients, but it came up in Calc 2, and that was a long time ago. And then I saw it and I pulled up Stewart. I pulled out my calculus book and was like, oh, okay. Well, this is like, it's clearly just like a given. Like when you're familiar with this stuff. Let's see if I can find it. Now this one's not going to be page 799. This one's not going to be the reals, but so this is, oh, no, this is a real number. Okay. Yeah, he doesn't prove it here. So let's back up a bit. He says one of Newton's accomplishments was to extend the binomial theorem. In this case, it's no longer a finite sum. It's a series. Fair enough. Okay, yeah, they just seem to be they're just doing it with Taylor series. Yeah, you can just prove it with Taylor series. I think that's why I didn't think about it anymore. It's just a Taylor series expansion. So it's like a Calc 2 thing. So like here's your original function, but the k, despite them using k, k is a real number in this example. Probably should have changed the variable. They probably should have called it y or something. But yeah, you can do a direct proof. It seems to just be Taylor's theorem. You know? So here's a formula for Taylor's theorem. Here's what you would get specifically for our function, this function, where k is real. So that's why Pólya doesn't even have a comment on this, because it's really not that complicated, you know? I was like, man, I feel dumb. I don't remember negative coefficients. But yep, you get this formula no matter what k is, even if it's real. If k is a real number. But the reason they're so adamant about this, the reason they're acting like this is so easy, is it's just Taylor's series. It's just a Taylor series expansion of that function. So they did it, and then they used the ratio test to prove that it would make sense if, so long as this ratio is less than 1, right? So long as you're plugging in x less than 1 into your function, but it also, I guess importantly, it also diverges, right? When you do the ratio test, it will diverge if it's bigger than 1. So that means that we're not going to be able to make any sense of this if x is bigger than 1. So you can plug in any real k that you want, but if you let if you let x be bigger than 1, you're going to have problems, which is a little funny. Like, why would that be the case, right? You can see it's not the case for positive k. Like, why wouldn't I, if I take x to be 2, I get 3 to the k. So what's wrong with that? So yeah, this only really, it only holds for certain if x is less than 1 in your formula. The series is supposed to diverge if x is bigger than 1. Which doesn't, right, that doesn't mean that the left side isn't defined, it just means that this is no longer the formula. Like this formula, well, first of all, it won't converge, so you won't make any sense of the answer. It doesn't mean that you can't plug in x equals 2 and k equals 1,000 or 10 or whatever you want. But yeah, isn't that funny? I also was like, I also saw that with a negative power and was like, I don't know what's going on here. I need to pull out the book. But then I saw this and I was like, man, how are they teaching this to like freshmen? Like, how would you justify this? But like, really pretty easy. Actually, it's Taylor series. It's a Taylor series. So they justify it the same way they did anything else that involved Taylor series expansions. If you can take a handful of derivatives, you can plug 0 into them. And then you have to check when it converges by usually do a ratio test. But you know, for some interval, at least a smooth function has a nice definition as a power series, including this puppy. And this one is called the binomial series. So yeah, that was a good question, Hitch. I also forgot why it was true for reals, but it's really not anything to be afraid of. And so then he just does an example, like this is a simple example. In fact, you don't even have to do it this way. You could just, there it is. That's what I was going to get. You could just look at a regular geometric series, but use negative x instead, and then you could take its derivative. And what would happen is a power would pop out. That extra power of n plus 1 would pop out, and it would be alternating. But if it's not this, then you're going to want, I mean, you don't want to do that every time. Like, what if it was to the 10? You're obviously not going to take 10 derivatives. You're going to want this formula. So, thank you all for popping in, watching my crazy ramblings. I think it's going to be another week of 27, 28. I'm going to try to bang this out next week.